So I want to thank the organizers for the opportunity of presenting this work that I've been doing in collaboration with Igor Ivanov from Lisboa and a postdoc from Colima, Enrique Jimenez. And I'm going to talk about general ICP and in particular, or at the end, the UCAWA interactions. So a word of warning, what I'm going to say has nothing to do with nature yet. This is some things that we've been playing around, trying to get to something in the near future. And basically the main motivation comes from a model that I will describe very briefly that was created by Silva and Ivanov earlier this year. So besides CPT, self-consistent quantum field theory, as you know, does not specify uniquely any discrete symmetries such as C, E, and T transformations. The analysis for the case of multiplicative factors is well known and is old, done by Feinberg and Weinberg. Later on, a few years after that, Lee and Wick generalized the results to non-abelian discrete groups. And more recently, Carruthers even made more restrictions on phase factors. Now, the freedom, when you have your quantum field theory, your freedom gets even larger in the case where you have several fields with the same quantum numbers. What I'm going to do now is I'm going to concentrate on CP transformation on scalar fields. So let's consider a set of scalar fields like this. And we're going to denote by Jx the following so-called generalized CP transformation. So this transformation, you do this, and you obtain this, where of course you get the minus sign in the x coordinate, the complex conjugate of this field, and a general n by n unitary matrix. This is what is called a generalized CP transformation. Now, the common wisdom is that Jx, the transformation that I just showed you, for any x, can play the role of the CP transformation of the model that you create. The reason for that is the also well-known result by these people that all experimentally observable manifestations of CP violation can be related to basis invariant combinations of input parameters that are CP violated. And this is what we usually do, and we take this for granted. However, it is interesting to note that a non-trivial x can have interesting consequences. Take, for instance, just applying twice this CP transformation, generalized CP transformation. You obtain this with no conjugation, and this just becomes a family space transformation. It turns out that in general, any unitary matrix like this can be brought to a block diagonal form, with blocks being either 1-by-1 faces or 2-by-2 matrices of this form. If it turns out that you use an x such that alpha is not equal to pi and therefore Jx squared is not equal to 1, then you don't have a order 2 transformation. Okay, so it's not set to plus or minus 1. Now, this has been known for a while, and those things are usually called high-order CP symmetries, and they are most of the time being looked at as merely a curiosity. The reason for that is that imposing a high-order CP symmetry led to models with other accidental symmetries, including order 2. And so it was like, well, what's the point? There is really not a path towards new models. You always end up with the order 2 CP symmetry. So people didn't take too much interest in this kind of analysis. There is an exception of a paper a couple of years ago by Shea and collaborators in which they made a classification of all high-order CP symmetries. And then they just claimed that this could perhaps be used in the future to create models or something like that. So that was an exception in the sense of the interest of going and analyzing high-order CP symmetries. This year, early this year, the first concrete example of a particular model which involved only multi-Higgs, a multi-Higgs model, with a Lagrangian invariant under a CP4, order 4 CP symmetry with no accidental symmetry was presented by these guys, Ivanov and Silva. And it was precisely the publication of this paper that got me interested in the subject, and we started working with it. So what they had is, they have a 3 Higgs doublet model with an order 4 CP symmetry, and they call it the CP4 3 Higgs doublet model. One of the doublets is the standard model-like boson, Higgs boson, plays the role of the Higgs boson, and the other two play a 2 Higgs doublet model with interesting consequences. Now, if CP is conserved, if this order 4 CP is conserved after electroweak symmetry breaking, the neutral physical scalars can be combined into complex fields, capital phi and curly phi, that transform under CP, under this order 4 CP, like this. So it's kind of a peculiar transformation. Notice that there is no complex conjugation. And they called it CP half odd. So I'm going to go through this to try to walk you through some of the interesting things that we've been learning about this. Or I've been learning, maybe you already know. The issue with this transformation is that you can ask several questions that we've been trying to answer. So for example, if you look at this just looks like a parity transformation. It looks like the C didn't do anything. So should we talk about P rather than CP? Is C necessary when we talk about neutral fields? Is a model consistent with this transformation? Is it detectable? Any CP violating effect is detectable in the basis invariant approach? Are there any signatures that are not compatible with the standard CP? These are the kind of questions that we would like to answer. We haven't, but we're working in that direction. So let's just remember what the standard CP transformation looks like. So here's a scalar. These things, these operators, states, correspond to particle and its antiparticle. That's the standard assignment. Okay. Now, one postulates, of course, that C acts on operators by just exchanging A and B, whereas P just flips the momentum. Usual stuff. And so in terms of the field, it looks like this. Now, I'm going to concentrate from now on the more relevant, physically relevant CP transformation, not C and P by themselves, since we know those are violated. We have chiral fields. Now, I can write this complex field in terms of two real fields, an even one and an odd one. And then, of course, each one of them has an expression like this. And so I can relate between the creation and annihilation operators of this one in terms of this one. So I call for H1, A1, and A2 for H2. Okay, since they are real, they have the same. And these are the properties under standard CP. Now, if the field is charged, it makes little sense to introduce H1 and H2. However, in the absence of any gauge interactions, working with A, B, or A1 and A2 is just a matter of convention. And this is important to realize. It's something we know, but I want to put it into the background so for what follows. Now, we all know that the exact form of the CP transformation law is basis dependent. And just to show you this, there is something very simple to do. Let's suppose we have this transformation under CP. It's an order 2 transformation. Now you make a basis change, defining a new phi prime just by I phi. And if you apply now the CP transformation on this field, you'll take this. So a rephased field transforms differently under the same CP transformation. And in this case, the role of H1 and H2 defined in by H1 prime and H2 prime to define phi prime are reversed with respect to the original one. So this is also a well-known result. I just wanted to put it here. It's the exact form of a CP transformation law is basis dependent. Now, I shows here a particular value for this, but in general, you can put any phase in it. And I want to stress that this is not a new CP transformation. It is the same CP transformation seen in a different basis. let's now look at what CP without conjugation means. Let's now consider two real CP even mass degenerate scalars. So they are both CP even. So that means they transform like this. I can still combine them to create a complex field in this way, which by creation, by definition, is CP even. So here it is. There is no conjugation. Now, what is the interpretation of this thing? It's just that phi is conjugate under CP, and thus under C. And so is phi star. Here the thing is that they are not related to the CP transformation. In terms of the operators, what you obtain is this. These are the operators for phi and for H1 and H2. And here given. And what you end up is with these and these corresponding to different particles, not particle and antiparticle. Okay? So CP even complex scalars cannot possess any conserved non-zero charge gauge quantum number that would tell particle from antiparticle. So if you define or if you need to use a complex scalar field without quantum numbers, then you cannot tell from one from the other. And then you can ask, well, so what? Why is this relevant or why is it important? Well, the thing is that it turns out that conjugated or not under CP is then a matter of basis choice. Let me continue motivating this. Consider now two complex scalars, phi 1 and phi 2. But now, the generalized CP transformation is this one. So now, not only conjugates it, but sends it to the 2, and vice versa here. Suppose they are mass degenerate, and that they have the same quantum numbers. Therefore, you can speak of a multiplet of complex scalars. In terms of the operators, now, you have these. A1, B1, A2, B2. And it turns out that, again, A1, 0 is not the antiparticle of B1, 0. Let's perform a rotation in the space of complex fields. So now I just rotate these two and define these two. Then I look at their CP transformation properties, and they have this, which looks pretty conventional. Okay? This is looks like a CP even, then a CP odd. It looks like. Where the real part of these and the imaginary part of this one are CP even, and these are the CP odds. Then I can redefine a capital phi field with these two and a capital phi tilde field with these two. And now these things transform like this. So I started with two real fields, and I end up with this thing right here. CP even and CP odd complex fields. No conjugation. Finally, we can express the passage from the original phi 1 and phi 2 to these weird fields, through this rotation. And so this is a basis change that undoes the conjugation under CP. So what I want to conclude with this part of the transparency is that in the case of gauge-blind complex scalars, like the ones I started with, the C transformation loses its importance or its meaning as a transformation that maps particles to antiparticles. It's as if it didn't exist. The space of fields acquires a larger basis freedom, basis change freedom. In certain bases, CP looks like P. Now, the basis change freedom, something that, again, I want to stress that I already said, but I want to re-say it, I will repeat it several times, is that it is the same CP transformation that appears as the standard one in one basis and as just a P transformation in another. So it all depends on the basis. We can continue to make this more exotic, and here is where we get to the original model that motivated this. This freedom allows us to consider even more exotic things, like, for example, this transformation, which is similar to the previous one that I just discussed, except that now there is an I. Notice that in this time, the CP transformation is of order 4. And so here we have J squared equals 1, and not equal to 1, and we have this. In terms of the creator and annihilation operators, we have this relationship, and we end up with the transformation doing the previous procedure that Ivanov and Silva obtained. They are CP eigenstates. However, now they are not plus and minus. You can have a quantum number Q defined modulo 4, and so this generates the notion of, generalizes, the notion of CP parity. And here are the charges for these fields, and Ivanov and Silva noted them as CP half-odd. They created that name, so I'm going to continue to use that name. I don't know if it's going to stick around, but anyways. And so now, the thing that we wanted to do is to see what would happen to fermions, coupling fermions to these kind of fields. And so in order to do that, we just explore a little bit the usual CP transformation, the standard CP transformation for fermions. These are the normal results of the bilinears. And if we do it for one generation, we just get the usual result. So there's nothing new. It's just the scheme that you use to produce a CP invariant Lagrangian. Now, what happens in the case of two scalars, where we have this extended basis gauge free? In that case, the Lagrangian gets duplicated with matrices A1 and B1. So let me go back a little bit here. This is the Lagrangian for the Yukawa interaction, fermions, scalars, and then you have general matrices here for NF generations of fermions. And so here, if we extend it to two Higgses, for example, then we have A1 and B1 for one of them, A2 and B2 for the other one. And if we assume this transformation that we are interested in, you get a condition on these matrices, and you get the expression for here, and that's it. Now, what we really want is to use the order 4 CP symmetry. In that case, if we assume that the fermions transform standard way under CP, and the scalar fields transform like this, we obtain this, which means that A is equal to minus A, B is equal to minus B, and this is, of course, no coupling. Nothing happens. And so the conclusion is that what we have to do is extend this generalized CP transformation also to the fermions. And in that case, requiring CP symmetry makes the fermions participate in family mixing. And those that participate in family mixing must be degenerate in order for CP to be conserved. We do the same analysis. We plug that into the Lagrangian, demand CP conservation, and this gives us some conditions on the matrices A and B, as well as the matrix Y. Y comes from the matrix here that is mixing the families. And for the case of three families, this is why it can always be brought into this form. And in order to have CP invariant case, there are only two cases. This is a rotation of this one, so it's the same case. There is another case. Notice that this is important because this is now order 4, this is, order 8, and this is order 4. But the places where we have non-zero entries are the bilinears that are CP invariant. So these are the Yukawas that are allowed. And so it has a particular effect on how the Higgses couple to these fermions. So an example, in the same model that they have, but now introducing fermions. These are not real quarks. I'm using just the notation for quarks, but these are the Higgs doublets, and these are some kind of fermions, chiral fermions. And we do the analysis, and what you observe is that you get these relationships that if you go back to this form of Y that I said you can always bring it to that part, you obtain these. And so you see that you have very particular combinations that are allowed. So we have constructed the CP conserving Yukawa's sector for this particular model, and after electroweak symmetry rating, where the first Higgs acquires a bed and the last two don't, and that's the model that they have. For illustration, you consider the lepton sector, and what you obtain is a Lagrangian like this. You also get two cases, and in the first case you get this. Notice these interesting terms in the Lagrangian. For case 2, well, here first, we can combine bilinears into CP eigenstates, and also the bilinears have the CP half-odd, and so they compensate the way that the scalars behave. And you obtain these two cases. In one case you get this Lagrangian, and in case 2 you get this Lagrangian. And I'm about to finish. This looks like lepton flavor violation, but remember that in the convention used here, the single fermion particle and antiparticle states are linked via the generalized CP transformation. And so fermion and antifermion operators belong to different fields. And so the decay of this field is not related to the decay of this field, and that shouldn't be surprising because they are not antiparticle of each other. However, fermions are charged. And so maybe we should use the standard, more physical interpretation that the fermion field contains the creation of a particle and the annihilation of its antiparticle. And if that's the case, the generalized CP-Yukawa interactions will be manifestly CP violating, despite the fact that CP is conserved in the model. And this is a very interesting result, and with that, I need to finish because my time is up. Just saying that another possibility, which is called C-agnostic, is that avoid assigning who is an antiparticle of whom. There is no C parity, and therefore this symmetry is just a peculiar symmetry linking different fields. The problem is that then what does CP violation mean? How do you explain baryogenesis and things like that? So wait and make a realistic model first. And this is what we want to do now. We want to go into a realistic model where we have actual quarks and leptons. And thank you.
How to generalize CP but only relation to
Lorentz symmetry. It's just CPT, right? So CP, how can I say this? If you have the quantum field theory, of course you have to have Lorentz symmetry, Lorentz invariance, and CPT are not part of that. So, but CPT has to be conserved in a quantum field theory. So, I don't know if that's a relationship or not, but I think they are separate things. So what we mean by generalized is that it mixes, just abusing language, it not only conjugates but also mixes families. That's what we mean by generalized. Usually when you just take a quantum physics book and a QFT book and you define the C transformation on the fields or the CP transformation on the fields, you just take the conjugate of the same field and change x to minus x. Generalizing that means if you have several fields with the same quantum numbers, you can also mix them. And you want to explore what consequences that has, observable consequences that has. Yes?
This looks similar to CP mu tau symmetry in the case of fermions. It's a very similar thing, and that concept now has been generalized in the case of fermions, in which you allow an arbitrary similarity transformation, arbitrary matrix transforming the original matrix to the so you can shuffle the fields by
so you start
in a more general way.
Okay, so you start imposing just mu tau.
I mean, mu tau symmetry was the origin, and now that method is called the residual symmetry method for studying the implications of CP. I mean, predictions for CP violation for the case of fermions.
Hi, if you have a question, you can start later. Best time is speaker again.